Welcome to the fourth lecture of module 3, which is on gas liquid operations, and particularly for equipments we will discuss in this lecture. In the previous lecture, we have discussed the equipment which are in which the gas is dispersed into the liquid, and that equipment particularly we have designed the tray tower design, and today we will discuss the liquid dispersed equipment. And out of these equipments, the important equipments which are useful for gas liquid operations are the Venturi scrubber, weighted wall column, and pack towers. So, in these equipments, the liquid is dispersed in the form of droplets or thin film. So, let us consider Venturi scrubber, in which liquid is dispersed as a droplet. So, we have a reservoir sorry. So, we have a liquid inlet at the top, and there is a nozzle through which liquid is dispersed, and gas in at the top, and gas out at the bottom, and the liquid out also at the bottom. So, this is very simple equipment, and in which the liquid is dispersed in the gas as a form of droplet, and gas is in the continuous mode, and this is very much helpful when the liquid contains dissolved solids. For example, absorption of SO2 from furnace gas with slurries of limestone. So, another equipment which is also very much useful for laboratory contactor is the weighted wall column. It is a vertical cylindrical tube in which the liquid is flowing as a film either outside of the tube or inside of the tube. So, and the gas flow may be co-current or counter current. To the liquid. And this is very much useful for laboratory mass transfer experiments, since in this case the surface area or the interfacial area among the gas and liquid is known, and we can vary the gas liquid interfacial area depending on the design of the weighted wall tower. So, this is the interfacial area is also our control, and this equipment is very much useful for laboratory mass transfer studies. So, here the liquid flows as a thin film. Now, we will discuss a very important equipment which is used for the industrially for the gas liquid operations is the pack towers, and it has two things we need to design for this pack towers. So, there is a liquid inlet at the top, so we have a liquid distributor so liquid in and liquid is distributed at the top on the packing surface. The packing materials are placed inside, and there is a redistributor in the middle for proper distribution. This is redistributor, and the gas out is at the top, and there is a gas in at the bottom, So, liquid out at the bottom, and this is a packing support which will take care of the weight of the packing. So, the packing, so in this case for packed tower design, we need to know different types of packings and how they are packed in the towers, what should be their criteria. The packing of the towers, and the second thing is the pressure drop in packed towers. So, these are the two important things we will discuss while designing the packed towers. And the packing, there are variety of packings used for the packed towers. And they are of different size. So, different size and shape, also different performance. The material used for this packing in general, ceramic, metals or plastics. And there are commonly two types of packing. Two types, one is random packing and second one is structured packing. Structured So, in random packing, it is the simplistic way of packing, just dump the packing materials through in the tower and let them settle freely through the on the packing support. And in case of structured packing, this is different variety of structured packings are available, and the advantage of structured packing is the first one is the low pressure drop, and second is improved capacity and efficiency. Capacity and efficiency. The disadvantage for this case, the structured packing, is that the cost is relatively higher cost compared to the random packing, and generally this packing are preferred where we need a specific arrangement in the packed towers. The random packing are also different kinds. This may be classified into three categories. One is first generation, packing, then second generation packing, and third generation. The first generation packing, which is two most commonly used first generation packing, are the racing ring and ball saddle. Racing ring are cylindrical in nature. So, this is the racing ring, and another one is ball saddle. So, this is ball saddle. The second generation packing is the interlocks saddle and pawl ring. And the third generation packing is generally lightweight, material like plastics and metals, and second one is less pressure drop compared to the other two generation packings, and the larger interfacial area. The most important thing for the packing is its surface area. So, the important characteristics for packing are the following. One is large surface area, which is desirable, high void volume, so that the gas and liquid flows smoothly without any interference, sufficient mechanical strength, uniform distribution of gas and liquid, and should be fouling resistance. So, these are the preferred characteristics of the packing, and another important tower characteristics is the liquid distribution. Proper distribution of the liquid at the top of the tower is necessary. So, that is what we need to use a proper distributor at different points. distributor at the top as well as different location of the tower. And if the distributor at the top of the tower is not properly installed, in that case the some portion of the tower packing may remain dry. So, if this is dry packing which is inefficient for gas liquid or for mass transfer. So, ideally the liquid should be distributed at infinite points at the top, and for this there are various devices are in use. One is V-notched channel, and second one is orifice, and third one is spray channel. So, these are used at different locations for distribution and redistributions of the liquid in the pack towers. Another important thing is the liquid hold up. There must be some reasonable liquid hold up to the bed which will facilitate the mass transfer. Reasonable liquid hold up is required for to facilitate mass transfer. If there is excessive liquid hold up, what happens? The pressure drop increases, and there is a possibility of liquid entrainment. And third one is decreases efficiency. Generally, the liquid hold up its permissible limit is around from few percent to 15% of the bed volume. The liquid holdup can be calculated from the correlations HL is 0.93 VL AP divided by G to the power 1/6 mu L square AP cube divided by rho L square G to the power 1/10 sigma L AP by rho L G to the power 1/8. So, this HL is the specific liquid holdup in meter cube of liquid per meter cube of bed volume. VL is the superficial liquid velocity which is in meter per second. AP is the specific surface area of packing. Which is meter square per meter cube. Sigma L is the surface tension of liquid. In Newton per second, Newton per meter. Sigma rho L is the density of liquid, kg per meter cube, and mu L is the viscosity of the liquid, kg per meter second. Now, we will discuss another important phenomena which occurs in the tower is the loading and flooding. When the liquid is flows through the pack tower down due to the gravity, the gas flows from the bottom to the top and the gas flows. So, if we consider counter current flow in the pack towers, counter current flow liquid from top and gas from bottom, liquid flows due to gravity and gas flows due to compression or the blower power. Compressor or blower. Then when the gas flows and the liquid also flows from top to down, the gas experienced pressure drop as it flows through the bed. The maximum area available for flow of the gas when the tower is dry. That means, there is no liquid throughput. In this case, we can see the, if we plot log delta p versus log g dash, the pressure drop for dry bed increases linearly with the gas flow rate. In the log plot, we can see it is for dry bed, and when there is a liquid flow from the top of the tower, there is a liquid hold up due to the void volume of the bed. Then the area available for the gas flow reduces, decreases the area available for gas flow, and so the pressure drop increases above the dry bed. Pressure drop increases above the dry bed. So, this is the pressure drop line for a particular flow rate of the liquid. This is with particular flow rate of liquid. So, the pressure, as we can see, the pressure drop for the bed increases linearly like in the dry bed, and after that period there is a sudden increase of pressure drop. This is when say point, this is M and N curve for dry bed, and this is at a particular liquid flow rate O, P, Q and R, these are the points. So, above point P, the accumulation of liquid starts. So, the region between P and Q, these points is known as the loading region. So, and also the point Q is known as the incipient of flooding. So, the flooding starts at point Q, where there is a sharp increase of pressure drop. So, above point Q, the accumulation of liquid in the bed increases sharply, and the region between, so the pressure drop increases, so the region between Q and R is known as the flooding region. As we can see, above point R, the column is completely flooded, and at that time the column may operate as bubble column. Above point R, column may operate as bubble column. Now, we will discuss the pressure drop in the packed hours. The pressure drop allowable limit for the packed hours should not be (1.2 kilopascal per meter of packing height). So, there are many correlations available to calculate the pressure drop in the packed hours, and there is a generalized pressure drop correlations obtained in the literature known as generalized pressure drop correlation, which is known as GPDC, and which is applicable for most of the random packings. And available as charts this will be available in most of the standard literature, standard books, and this chart has two parts. One is flow parameter and other one is capacity parameter. the flow parameter which is designed by given by M and defined by L dash by G dash into rho G by rho L to the power 0.5, and the capacity factor which is N is equal to F P V F S mu L to the power 0.1. L and G, these are the gas flow rates, liquid and gas flow rates. Rho G and rho L is the density of the gas and liquid. F P is the packing factor, and which is F P by epsilon cube, and A P is the packing interfacial area and epsilon is the porosity or the void fraction. V F S, we can calculate V F S is equal to V S G superficial gas velocity into rho G by rho L minus rho G to the power to the power 0.5. So, V S G is the superficial gas velocity, and the capacity factor can be calculated at flooding conditions from the following correlations: ln n flooding is equal to minus 3.5021 plus 1.028 ln m plus 0.11093 ln m square and the capacity factor which we have defined earlier in this case F P. So, packing factor F P is in feet square per feet cube, and the viscosity of liquid in Pascal second. So, we can calculate the pressure drop for the packed towers, and there is a correlations proposed by Kister and Gill in 1991. So, that correlations can be used delta P by L at flooding is equal to 93.9 F P to the power 0.7, and the unit of this is Pascal per meter of packing height. So, and F P is unit of, as we have said, F P is feet square per feet cube. Now, usually the packed towers are designed based on the any one of the two criteria. Usual design, a fractional approach, to flooding gas velocity or second approach, a maximum allowable gas pressure drop. Now, for a given liquid flow rate, and properties and the packing material for a given packing material, we can calculate in flooding and then we can use this one to calculate VSG, and then we can assume the second part, we can assume the flooding for say around between 0.5 to 0.8 packing flooding factor, and then we can calculate the diameter of the tower from this equation. D is equal to 4 Qg by F V S G F S G to pi to the power 0.5. Now, let us consider the example we have considered for the plate column design. The same example if we consider in this case for the packed tower design, only we have to mention the type of packing used and what is the packing factor for this case. Then we can see how to calculate the diameter of the column requires and the pressure drop. So, ammonia is absorbed by pure water from air ammonia mixture using a packed towers. The mixture contains 10% ammonia and 90% air. It is desired to remove 90% ammonia. The gas enters at the bottom of the tower at a flow rate of 150 kilomole per hour at 290 Kelvin, 98 Kelvin and 1 atmosphere. The water is fed at the top of the tower at a flow rate of same as gas 150 kilomole per hour, and the molecular weight of ammonia is 17, air is 29. The density and the viscosity of the liquid is 1000 kg per meter cube and 0.845 into 10 to the power minus 3 Pascal second. Use 15 millimeter metal racing ring as the packing materials and the packing factor Fp is 170 feet square per feet cube. Design the tower for an 75% approach to the flooding velocity. Now, for the gas inlet, let us calculate the parameters which are given. Mg average is 0.1 into 10% ammonia plus 90% here. So, this is 27.8 the gas flow rate we can calculate 150 kilomole per hour into 27.8 divided by 3600. So, which is equal to 1.158 kg per second. Rho g is PT total pressure mg average by RT, which is equal to 101.3 into 27.8 divided by 8.314 into 298 Kelvin, which is equal to 1.137 kg per meter cube. Qg, the volumetric flow rate of the gas, is G dash by rho g, which is equal to 1.158 divided by 1.137, which is equal to 1.019 meter cube per second. Now, for the liquid exit, we can calculate the parameters. The ammonia absorbed is equal to 150 is the flow rate kilomole per hour into 0.1 plus into 0.9 into 17, which is equal to 229.5 kg per hour. And L dash is 150 into 18 plus 229.5 by 3600. So, this is equal to 0.814 kg per second, and density of the liquid is given 1000 kg per meter cube at 298 Kelvin. Now, we can calculate the flow parameter. M is equal to L dash by G dash rho g by rho L to the power 0.5 is equal to 0.814 divided by 1.158 into 1.137 divided by 1000 to the power 0.5. So, this is 0.024. Now, ln flooding n flat we can calculate minus 3.5021 plus 1.028 ln m plus 0.11093 ln m square. So, if we put the value of m, this will be minus 1.211. So, n flat from this will be exponential minus 1.211, which is equal to 0.298. Now, for 15 millimeter racing ring, metal racing ring, Fp is given, which is 170 feet square per feet cube, and mu L is 845 into 10 to the power minus 3 Pascal second. So, we know that n is equal to F p V F s square mu L to the power 0.1. So, V F s we can calculate n flat divided by F p mu L to the power 0.1 to the power half. So, this will be 0.298 divided by 170 into 0.845 into 10 to the power minus 3 to the power 0.1 whole to the power 0.5. So, this will be equal to 0.06 meter per second. So, now we can calculate the VSG is equal to VFS divided by rho g by rho L minus rho g to the power 0.5, and this is substituting these values. This is 1.77 meter per second. So, delta P by L flat at flooding, the pressure drop we can calculate 93.9 into 10 to the power into F p is 170 to the power 0.7, which is 3412 Pascal per meter of packing. So, the flooding pressure drop we can calculate. Now, we can calculate the diameter. F is given 0.75 and D we can calculate 4 q g by F V s g into pi to the power half. So, substituting 4 into 1.019 divided by 0.75 into 1.77 into pi to the power 0.5, which will be around 0.989 meter. So, this is the diameter of the column required for the particular operations. So, this is end of lecture 4 of module 4, and this is the last lecture. In the next lecture, we will discuss the absorption of certain component into the liquids, that is absorption module 4. Thank you.